Okay, and so I'm just going to start back here in the home directory just as a quick reminder of how to get to the Jupyter book, in case you missed that earlier. So once you're in your home directory here, you'll see a workshop Jupyter books directory. Click into that. If you click the Jupyter book button here, you'll notice that you don't have a book because you're not actually inside the book yet. You actually have to open up the Jupyter book. And then once you're inside of it and you can see the table of contents and config and everything, then you can click the Jupyter book and open that up. And so I'm going to be demonstrating use of OPERA RTC data to calculate a coefficient of variation. But I don't have this data pre-staged, so I'm going to download this, this from ASF using ASF search, the ASF search Python tool. And so there are a couple of notebooks here in the OPERA data access section of the OPERA chapter. They're very similar. One is for accessing RTC and one is for CSLC. I'm not going to show the CSLC one, but it is very similar to the RTC. And if you follow along with the RTC, you'll know how to use the CSLC version as well. So we open this notebook up and start running the code cells. And of course, we have to, we're downloading the data, so we have to authenticate with our Earth data credentials, Earth data login credentials. And if you've done this correctly, then you'll get this little success message. And then this just asks for you to provide a name for the data set that you're going to be downloading so that it can create a directory in which to store those data. The area that I've searched in this notebook is over the Ghazipur region in Bangladesh. So I'm going to name this Ghazipur BD demo. And now that I've run that code cell, I should be able to go back here to my home directory. Did I not create it yet? Oh, here it is. Yeah, so it's not in the home directory. It's alongside the Jupyter book in the workshop Jupyter books directory here. So it's made this empty directory that I'll eventually download the data into. And so there are a couple, well, there are a number of different ways to search using ASF search. And so this is just a quick demonstration of a search using the OPERA product ID names. So if you know the specific names of the products that you're looking for, you can do a granular search on those product names. And then I've printed out the results here. But perhaps a more typical use is to do a geographic search over your area of interest. And so that's what I'm demonstrating in the code cell below. And you'll see that I have selected a number of options. So I've provided the intersects with argument, providing some well-known text to a point. So it will find any OPERA data intersecting this point. Well, and I've identified the data set as OPERA S1. I provided a start and end time. I provided a flight direction, and the processing level of product is RTC. However, there are many arguments that you can use when searching ASF search, and I've listed them all right here. And so you can use any combination of these that fits your particular search. So I'll kick this off, and it has found 12 RTC products with one burst ID. It's possible that multiple burst IDs may have intersected this path. And so if you can download all of those, all the data for every burst, or if you'd like to limit it to one, then you can just select one in here. But this little, perhaps this isn't the best example because there's only one option in here, but if this had, say, 5 different bursts, you could select all of those using the shift button, Or using the control button, you could select one or many of those. So you can make the specific set of bursts that choose the specific set of bursts that you're interested in. And so it found all of these. It found these products, and there's something to note about these data. So currently, I believe this is an issue both with RTC and CSLC Opera products in the ASF archives. Some of them are being doubly ingested. So we're getting a product that has incomplete metadata, and then within a matter of seconds or minutes, a complete version of the product. And so that is something to be aware of, that we are working to fix. But if you're searching for data, you may encounter instances where you have two products that were acquired at the exact same moment and have the only difference in the product is that you can tell from the file name is the difference in the processing date, which may only differ by a few seconds. And so all I'm doing here as a sort of a temporary workaround to this issue is searching for is only grabbing the most currently processed product if two products are identical. And so you can see that it has reduced the number of products that it's going to download here. And I shouldn't see any, in each of these Opera product IDs, the first date here is the date that the data were acquired, and the second date is the date that they were processed. And so once I've run this code cell, I should not see any duplicates in my acquisition dates. And so this now we'll actually download those data, and this will take just a few seconds or a minute. And when we finish downloading this, you'll notice that we have all of the RTCs. However, we don't have any of the static layers. And so we actually have to search and download those separately. And so, okay, so this is completed. So we now have all of our RTCs downloaded, and they're each stored in their own directory. And so here you can see the VV or the VH and the VV and the layover shadow mask and an H5 file filled with metadata and some more metadata in this XML. But we don't have the static layers. And so that requires searching at the processing level of RTC static. And so here I am just looping through those filtered bursts where I've removed the duplicate products. And so I'm going to download just a set of static data for each burst. In this case, I'm only working with one Opera burst here, a number of products all within the same burst. And so once this finishes downloading, we'll see that I have these static layers, which apply to all of these products in this burst in T114, 242, 855, IW2. This is the burst ID. This T through 2 here is the burst ID, which you'll also see in all of the Opera RTC product names as well. Okay, so now I have this small data set downloaded. And I'm going to head back to the Jupyter book. And now I'll open up the Opera data recipe section and select the Opera RTC S1 coefficient of variation user supplied dataset notebook. Okay. You'll see that I've saved all the output in place. I personally find it confusing to leave the output in place when I'm about to run a notebook, because I get confused over whether I've run a cell or not, because it gives you a little indication of the order in which you've run these cells. And if you just start running a notebook that's already been run with the output in place, it just replaces it with the same number. And so it's easy to lose track of what you've actually run. So so this is completely optional, but I prefer to come up here and restart the kernel and clear outputs to all cells when I'm about to start running a notebook. And once again, just like all of the other notebooks in this Jupyter book, this notebook uses the NISAR EA Workshop 2024-1 Conda environment. So you should select this Conda environment's kernel if it's not already selected. So now I can start running through this notebook, and at first we just make sure we're in the right environment and import the needed Python packages. And then we need to select the data that we'd like to look at. So I downloaded that data over Gazapur. So I'm going to go find that data. So it's here in Gazapur BD demo. And then, oops, I kind of went through that fast. And then I have to click into the burst I'm interested in looking at. And here you can see I've got all of my Opera products and the static layers. And so once I'm in here, I'll click the select button. One thing to notice is that when you use a widget like this and you actually have to select something in the output, the JavaScript of a code cell, you've clicked yourself back into that code cell. And so if I were to just rerun this code cell again, it's just going to ask me to select the directory all over again. So I'll do that here just to demonstrate. But what you should do is once you've selected that directory, you have to physically click into the following code cell, and then you can resume running it. And that's true just in general of any code cell. So with a widget. So here here is a widget asking us to select the polarization to look at. It came pre-selected with, defaulted to VH. And if I wanted, I could just continue running at that point. But if I wanted to select the VV, once again, I'm back in this code cell. So if I just hit the play button now, it's just going to reprint that widget. So if you click into a widget, you have to click into the following code cell to run it. And that's just a truism of Jupyter in general. If you're working in any Jupyter notebooks anywhere, you're going to encounter that issue. Okay, so I've selected the VV polarization, and it's gone out and found all of those VV TIFFs. And it's also found all of the H5 files containing the metadata associated with those RTCs. Now we'll collect the acquisition dates. In the notebook that Andrew just demonstrated, he also gathered all of the acquisition dates, but you may remember that he was able to pull those straight from his search results. However, in this notebook, because we didn't actually perform the search for the data here, we have to find that data a different way. We could either use the ASF search package to look it up by product ID, but in this case, I happen to know that the acquisition date is part of the file name. So it's much easier to just go and grab these files and do a regex search for the date in that file name. And also similarly to what Andrew did, I'm then populating all of this information into a pandas data frame. So I'm not actually really using this data frame in the notebook, but I think it's really good to show that this is something that you can do, because if you have a huge set of data and you're looking at different subsets of those data at different times and trying different things out, having them all of the file information and potentially geometries and everything in a data frame, in a pandas data frame or a geodata frame, allows you to very easily filter those results and pull the paths to just the data that you care about at any particular moment. All right, and so now I'm here. We open up the H5 file, or the first H5 file in the stack anyhow, and from that we grab the extents of the data and the projection of the data, and we do that in order to to create, well, I guess actually we do that later in order to write these out to write some of our results out to GeoTIFF. We need that information. But first, we're going to create a virtual raster table using GDAL, containing all the layers from the DVs. And this is just a little, sorry, this is a little pandas time series of the dates. And now we can look at just a couple of layers that we have. So there are 9 bands in total, each containing this number of pixels. So 3,435 times 1,527. And we can display a couple of these as plots and histograms of their amplitude returns. And so this is just to get a quick little view at a couple of the scenes that we've downloaded. And you can, depending on your particular data set, you might want to adjust the min-max for these in order to provide nice output in the plots and in the histogram there. So we don't need to convert from dB to power for Opera data, but I did include this just in case in case you're working with a different data set, just to be aware. You should be performing your calculations in power. And so at this point, we can create a little time series. And so this will show us just an animation. So this will pop up. Here we go. And so we can just run this animation and see how things are shifting over time. And so this is in the eastern part of Bangladesh, and it's in October through January, and so we can see most of the change that we see is going to be involving the the water on the ground here. And so so if you pay attention to this little spot right here, for example, and also this spot here, there are a number really. You'll notice that that as I step through, the water is starting to dry up. Like this is drying up, and these this area here, oops. Okay, so right now we can see this little river or stream and or swamp, and as we work through time, we can see that the water is is dissipating from that, and then possibly coming back a little bit towards the end. And so we can save that animation as an animated GIF. And then we can convert to dB scale and plot the both the original data in dB scale, and we can also perform a Savitsky-Golay filter to smooth those data out and try and identify a general trend in the data. And so you can see that there were probably some outliers in here, and so this really kind of smooths it out and shows us maybe a trend that might be hidden if you're just looking at the original data set. This function is for creating a GeoTIFF from the plots that we'll generate. Okay, and then we can calculate the coefficient of variation here and plot it, and then we'll also threshold it. And so one thing that I'd like to point out about this is, so the opera data contain nans all around the border, and which is why we're seeing this runtime warning. So don't worry about this runtime warning. It's expected. I added a little note about it here. So you can safely ignore that warning. And so here is our unthresholded coefficient of variation. And then we can write that out to GeoTIFF using that little GeoTIFF from plot function. And then we can threshold it. And so we are thresholding it to an alpha of 0.95. So that's the original. Okay, and here we're thresholding it. All right, and so here is our thresholded coefficient of variation, and so you can see the places that experience the most change over our time series. And there are a number of ways to to perform change detection analyses. The coefficient of variation is only one, but it has a benefit to it in that it is a unitless value. So once you've divided the standard deviation by the mean, you end up with this unitless value that's very then easy to compare with coefficients of variations from other data sets. So in a forum where we're introducing new and on the horizon data sets, this performing a threshold of or a coefficient of variation could be a useful way to compare the change detection with other data sets that you have available. And then once again, we can output that to GeoTIFF. And so now if I head back and look at the output here, all of my plots and animations that I've saved are here. And I've also got that virtual raster table that I created.